Thank you very much, and I would like to thank the organizers for inviting me. I am myself from Kyiv, and it's a great honor to give a talk here, actually, for the first time after 15 years. And so, I've been looking at the program, and I was somewhat disappointed because I realized that I'm actually the only pure Ab-initio person in this conference. Not taking into account Hirosinova, who also has a big model background, but I'm really hardcore Ab-initio guy. And therefore, I thought instead of delving into one specific problem, it's probably good to just give an overview of what Ab-initio is and what it can do in the field of spintronics, in particular in the field of topological spin-orbitronics. And if we talk about spintronics, many of you have heard or have seen this kind of magnetic hard disk, which actually revolutionized our understanding of technology and information storage. And if you look at the basic principle of operation of this guy, you will see that basically everything is reduced to magnetic bits, the state of which is manipulated and the state of which is read out by the electrical current. Now, the modern technology, of course, poses us different challenges with respect to these bits and currents, in particular generation, transport, manipulation, and detection. And we have various new design goals where we would like to have our devices small, robust, ultra-fast. We would like to have pure electrical control, and we want to have everything very cheap in terms of energy. And actually, surprisingly, at the same time that we have these challenges, there is a whole bunch of effects, some of which are listed here, which are closely associated actually with spin-orbit interaction, and which are believed to bring us closer to realizing these goals. The corresponding branch of spintronics is called spin-orbitronics, and as you know, spin-orbit interaction is a rather small interaction as compared to many other interactions, and therefore everything basically happens on very small energy scales. And what becomes clear at such scales is the importance of materials and functionality design, in particular with the focus on realistic simulations of complex materials. Besides that, there is, of course, leaving aside the technological aspect, there is a deep fundamental motivation, since many of these effects are actually united under the same roof based on the concepts of geometry and topology, which actually effectively brings them closer to such distant fields as quantum field theory, molecular physics, and nuclear physics. And I will try to show you on a couple of examples what does it mean and what can we do here with Ab-initio research, actually. To do this, I will choose skyrmions, spin-orbit Zoloshinsky-Murray interaction, Hall effects, and laser excitations. Now, geometry and solids. We have heard a lot about this already in this conference, and when we actually think of a solid, it's a family of electrons which lives on a certain manifold, on a certain object, and commonly in solid-state physics it is the K-space which this donut stands for. However, we can also have real space where our electrons live and where they move and where we can describe their wave functions. Now, the key quantity which actually characterizes how these electrons are glued together on this manifold is known as the Berry curvature, as Justin has introduced in the previous talk. And actually this is a quantity which couples two independent gradients of my wave function with respect to two different coordinates on this chip or on this manifold. Now, in a simple picture, Berry curvature is nothing else but a magnetic field, so particles' field curvature is a magnetic field. And now applying the principles of Aharonov-Bohm effect, we can say that when you have a wave function which propagates along a certain path in this manifold, or say in K-space, it acquires in this magnetic field a phase which is known as Aharonov-Bohm phase, and which we know in quantum physics as the Berry phase. What is even more interesting or more fruitful is that this Berry curvature determines the electron dynamics in a very simple picture. It is the same effect as the curvature of a cup would determine a trajectory of a ball, which actually moves on its surface. Very simple. Now, this is the expression for the curvature, general, and in solids, as I said, it is the K-space which is responsible for generation of this non-trivial Berry curvature. This particularly concerns the ferromagnets with spin-orbit interaction included. Now, in terms of a ball on the surface of a cup, it is very easy to understand the meaning of the Berry curvature as kind of a response quantity. we can think of a process where we ignite a motion of an electron, let's say with an electric field, and this is the part which stands here in the Berry curvature. On the other hand, we can look at the response of the wave function along an orthogonal direction. This is ky in the reciprocal space. And if this quantity is non-zero, we can actually ignite this coupled kx, ky dynamics, and like this we can understand, for example, the notion of the anomalous Hall effect, where we launch electrons with an electric field in a sample, and then we observe a transverse charge current, and the same applies for the spin Hall effect, where we have a spin degeneracy, and we therefore obtain a transverse spin current. Now, this is a general statement. If we have some electrons living in general spaces which have complex geometry, complex curvatures, we can expect actually complicated coupled dynamics of these electronic systems. Now, what we have heard in Justin's talk actually is that in the K space, when we consider the velocity of our Bloch electrons, the curvature leads to this anomalous velocity term, which is proportional to the electric field and the curvature itself. And now to obtain the conductance, the whole conductance in our sample, we just have to integrate this anomalous velocity over all states, and therefore we can think of this whole conductance as actually a flux of this curvature through the manifold of occupied states. And actually in insulators, there are beautiful mathematical theories about that the flux of the Berry curvature is quantized, and this leads to the quantization of the whole conductance. And with this quantization is associated the discovery of various topologically non-trivial phases, such as Chern insulators, topological insulators, and so on. And actually for this discovery, these three guys has got a Nobel Prize in physics just 1 week ago. Anyway, the K-space topology physics is really a turbulent field where a lot of things are happening, as we have seen, and we will still see in the session, for example, which leads to the Hall effects, which gives rise to various topologically non-trivial phases, and which enters even such fundamental properties as spin magnetism or orbital magnetism. However, what is becoming more and more fashionable is to put our electrons into more complicated environments, where we live not only in the K-space, but we couple it to different other parameters, such as, for example, magnetization direction. And in such complicated spaces, from such complicated topological arguments, we can actually understand a lot of physics which stands behind such fundamental phenomena as magnons, phonons, spin lattices, fermions, torques, and so on. And this is really an exciting and developing field of research where we try and we should try to contribute. Now, an important aspect here is actually the crucial role of a material aspect. Why is that? If we take a look at an electronic structure of the simplest transition metal, such as HCP cobalt, we will see that it actually looks rather complicated. In particular, if you try to calculate the curvature here, you will see that it is rather difficult because a lot of physics here is governed by the band degeneracies, where we have so-called Dirac monopoles which give singular contributions to the Berry curvature. Now, you have to treat these points very precisely if you want to reproduce any sort of data, or if you want to provide some reasonable estimates for the effects. And ideally, in our solid, we would like to solve, of course, the Schrödinger equation. However, this is actually a physical impossibility even for simpler systems, because in this case we know that we need at least a Milky Way to store a many-body wave function, let's say, in BCC iron. This is definitely not a good way to go. And what we do, we use the so-called density functional theory, which is an effective single particle theory, which reduces everything from the many-body wave functions to the charge density of occupied states, which is just a three-dimensional vector in real space. Now, to deal with this density functional theory, there are a lot of methods how you can approach it from this point or from that point. In Jülich, we have our homemade code FLIR, which we use extensively, and which combine with the supercomputing power that we have in Forschung Zentrum Jülich. We are actually able to calculate these things precisely, compare them to experiment, or make some material predictions on which effect should be prominent or which effect should be suppressed. What is also important to understand is that actually this Berry curvature does not come from the sky, but it can also come from more general arguments such as Kubo linear response theory. For example, you can write an expression which is well known from the 60s for the electrical conductivity in our sample, which is an expression in terms of the velocity operators and in terms of the Green's functions of our material. Now, you can start working with that, and this is also what you do, or we do, because the Green's functions give us an ability to include a disorder into the system. And disorder is an extremely important element in all these transport studies. Now, our activity is largely associated with development of numerical methods which allow us to solve these equations in various situations. For example, in the limit without disorder, you arrive at this notion of the Berry curvature rather rigorously. It is a well-known result. However, you can consider, for example, single impurity scattering, which then via the Boltzmann theory you can use to calculate the skew scattering contribution to the anomalous Hall effect or all other effects. You can even stay somewhere in between and use some simple models for disorder, such as, for instance, Gaussian disorder, which gives rise to so-called scattering-independent Hall effects and scattering-independent contributions to various things. So at the end of the day, what happens is that you end up with a whole toolbox of methods and numerical tools which allow you to treat various materials in various situations for the purpose of various effects. So let me give you an example of how this works. And the first one I would like to start with is the example of chiral magnetic skyrmions. In this conference, we have heard already about skyrmions, and we probably know by now that they actually come from nuclear physics. However, what is very surprising is that actually chiral magnetic skyrmions are on a regular basis these days observed in materials of various chemical and structural nature. And by skyrmion in such systems, I mean the localized distribution of magnetization in our samples, which has certain properties. Just let me come to this in the next slide. And actually, the skyrmion physics is becoming one of the flagments of the research in magnetism, because the skyrmions are envisaged as new particles for spintronics, which you could try to use for data information, transport, and storage. And this is associated with a number of fascinating properties that they actually have, such as high stability. You need low currents to move them around, there is suppressed scattering and effects, and so on. And the understanding here is that many of these fascinating properties have to do with non-trivial topology of skyrmions. So how does this topology actually enter into the skyrmion physics? Let's consider a skyrmion, and let's consider an electron which propagates through the skyrmion. And let's think in adiabatic picture language. So this means the spin is always aligned with the local magnetization direction. So what happens in this case, you can solve this equation analytically without spin-orbit interaction, is that an electron will pick up a Berry phase in the spin channel. So if it picks up a Berry phase, this means that we have some effective magnetic field, effective curvature in the real space. And this is known as an emergent magnetic field, which I denote here B. What is special about skyrmions is that the flux of this effective magnetic field is quantized when you integrate it over a skyrmion. And this is actually the feature which gives rise to all these robustness things. So you can tweak it all you want, but the field will be quantized. There will be one unit of flux or more, depending on what kind of skyrmions you have. But therefore, it is so difficult to destroy these particles. Now, another consequence of the presence of this field is that it exerts a Lorentz force on propagating electron. This Lorentz force, since it comes from the magnetic field in spin space, effectively is spin dependent. So what it does, it deflects the electrons of opposite spin to opposite directions in transverse direction. This is what is known as the topological Hall effect. This is a simple concept which we basically drew out of our fingers based on general kind of geometrical arguments. Now what you can do is you can try to use the Ab-initio or first principle methods to prove whether actually it means anything or not. And this you can do for complicated compounds, for example, such as manganese iron silicide alloys. This is the work we have done in collaboration with Christian Fleiderer's group, where they looked at this skyrmion phase in the phase diagram of these alloys. And what they did, they actually measured the contribution to the Hall effect as this bump, which they interpret as the topological Hall effect. Now, we compare their experimental measurements with our theoretical calculations, which take the magnetic field from their experiment and calculate basically the Hall effect which the electrons experience in this situation. And what we see is a very nice agreement between the two sets of data, which actually allows me to say that indeed there is topological Hall effect, and it comes from what we think it comes, and that is a main tool to detect the skyrmions. All right, so this picture I drew without spin-orbit interaction, and without spin-orbit interaction, if I look at the orbital degree of freedom in my skyrmion, I will see that it is not at all affected. So you see here, basically, there is nothing. With spin-orbit interaction, what happens is that the electronic wave function, the orbital part of it, becomes coupled to the magnetization direction, and therefore to the real space. So basically, spin-orbit interaction causes ripples in my electronic wave functions in such skyrmions. In reality, in the simple picture of a ball propagating on the surface of a cup, my electron now moves on a very complicated profile, on a very complicated cup, which lives both in reciprocal K and in real R spaces. And the thing of this cup is that it has a complicated curvature tensor for curvature. So the real part, this part here is what is the emergent field is about. This is our anomalous Hall part, and this is what we call the mixed Berry curvature, which actually couples the geometry in both spaces. Now, actually, we know what we have to do when we have particles which move on a curved surface, and in this case, the geometrical arguments again give us some kind of clues as to what we should expect. And not only that, they also give us clues as to how we can calculate these effects. For example, we can calculate the changes in the energy of electrons, which are caused by this curvature tensor, and we can compute this, we can derive the expressions, and in this plot you see the plot of this energy contribution due to skyrmion in manganese silicide, these so-called ripples in electron energy. And from phenomenological arguments we know that this can be attributed to nothing else but the Zelensky-Murray interaction. So the Zelensky-Murray interaction, let me come to it briefly, is one of the most fundamental interactions in magnetism. It is the consequence of magnetism, of spin-orbit interaction, of broken inversion symmetry, and as we have discovered recently, of geometry as well. Zelensky-Murray interaction is a beautiful interaction because it actually allows you to distinguish between states of different chirality based on energetic arguments. For example, the non-zero DMI for these two spins would energetically prefer either this state or its mirror image. In a sense, the DMI is something which allows us to distinguish the left hand from the right hand, and in this sense, it is a rather natural concept. Now, since we have now a preferred chirality, we can also expect that we can have formation of chiral spin states in magnetic systems. And for example, this is true for these iron biatomic chains on iridium, where in the collaboration with the Wiesendanger group, we were able to disentangle one of these spin spiral states. And the calculations which we do can allow us to predict the exact spin structure which occurs in this system, and this is actually the 120 degrees spin spiral. Now, the DMI is also important, as you probably know, for the physics of chiral domain models and magnets, but it is also extremely crucial for the physics of skyrmions. In particular, it allows to distinguish between skyrmions of different sense of twisting. So some of the skyrmions with twisting like this will be favored over the skyrmions with twisting in the opposite direction. And here, with our calculations, we can actually understand why some systems exhibit a certain preference towards twisting in a certain direction, as exemplified on the example of these manganese iron germanium alloys, where not only the magnitude of DMI is comparing to experiment very well, but even the change of sign of the DMI, which is experimentally observed by the Kura group, is reproduced precisely. Moreover, we can even understand from which electronic transitions this change of sign happens. Okay, let me come to another example, and this is an example of spin torque. Many of you have heard about the spin transfer torque, or you probably all know about it. This is where we use a magnet to polarize a spin current, and then we inject it into the region with a different magnetization direction. And what happens is that this magnetization of this free layer experiences a torque from the spin polarized current, which is exerted from somewhere. This is an effect which relies on non-collinear physics, and it is actually technologically used to control the magnetization in so-called STT MRAMs. Now, within the phenomenon of spin-orbit torque, we can actually switch the collinear magnetization in a ferromagnet just by applying an electric field. And this is an effect which relies purely on spin-orbit interaction. Actually, the deterministic switching of the magnetization in systems of this type, like thin layer of cobalt deposited on a heavy substrate with reasonable current densities, has been demonstrated. And even recently it was suggested that you can use this spin-orbit torque effect to move chiral structures, such as skermits. Okay, let's think in simple terms. How can we understand this effect of spin-orbit torque? What I mean is that let's try to find the curvature which would give us a desired response. And let's consider, just for simplicity or for exemplification, such a system of a ferromagnet deposited on a substrate. Magnetization is out of the plane. Now, if you play around, or if you think, or if you do calculations, you will discover that it is the curvature of this type which is non-zero in such a situation of a ferromagnet with spin-orbit interaction under the condition of broken inversion symmetry. And what I mean of this type is that one coordinate stays for reciprocal vector k, and the other coordinate stays for the magnetization direction in our sample. Now, in this simple ball on the cup picture, we can now apply electric field, and we can ignite the motion of our electrons in k space. What we see actually is a response in the magnetization direction. And this is nothing else but the torque which we apply with the current. So what we can conclude from this simple picture is that the spin-orbit torque is a result of complex geometric coupling that we can have in these systems. What we can also conclude from knowing the physics for, let's say, of anomalous Hall effect is that the physics here is driven by the monopoles, but not in the k space now, but in a combined space of k coordinate and the magnetization direction. Now, to be a little bit more formal, we can define the torque which a current E exerts on the magnetization in terms of this tensor which we call torquance, in analogy to conductance, which we know from electrical transport. And what we can do, of course, we can calculate now spin-orbit torques in various systems based on these curvature arguments. However, what else we can do is we can apply the Kuba linear response theory in the spirit of what we did for electrical transport to study the influence of disorder on spin-orbit torque. And what we discovered by doing these calculations actually is that in one component of the spin-orbit torquance tensor, which we call even, we acquire a constant value of spin-orbit torque for all the systems that we study as the disorder goes away. So there is definitely a contribution without disorder to this effect, and this basically proves that there is Berry curvature physics in this phenomenon. What we also discover is that in the other component, which we call odd, there is a divergent part of this spin-orbit tensor, and this is actually an analogy to electrical conductivity, which we know diagonal part of electrical conductivity, which we know diverges with vanishing disorder. Now, these two types of torques have been experimentally observed and discovered, and their existence has been actually demonstrated. And what is important is that these two types of torques are not only different in their disorder dependence, but if we take this typical system, magnetization here, electric current here, they are also different in the way, in geometrical way that they act on the magnetization. The even torque is perpendicular to the plane of the current and magnetization, while the odd torque lies in it. The same applies to effective fields which we can define to act on the magnetization on such a situation, and they also behave differently. Now, this of course very nice. However, we can also use our knowledge of the wave functions and ability to compute various operators in Ab-initio theory to prove or to demonstrate that the even Berry curvature part of spin-orbit torque actually largely comes from the spin Hall effect, which is generated in the substrate, while the other part of torque is largely dominated by interfacial effects, in particular in the sense of spin accumulation which occurs there and which is known as the Edelstein effect. Therefore, we call it an Edelstein effect torque. And I think this is something which some of you have heard also in the talk of higher synod. Okay, what we can also do is we can suggest novel classes of materials which could be promising for spin-orbitronic applications. And here I would like to give you an example of antiferromagnets, which by now have been believed to be actually rather useless because they don't exhibit any macroscopic magnetization. However, let's take a look. And in the first study with our collaborators from Argonne, Axel Hoffman, we have shown that antiferromagnets, although they have vanishing magnetization, they can give rise to large spin Hall effect. And the spin Hall effect can exert a relatively large torque on a ferromagnet if you bring in contact with it. Now, what we asked ourselves then is whether an antiferromagnet can exert a torque on itself, so to say. And what we knew from model studies is that you need some sort of staggered fields which act on staggered components of our magnetization. If we take, for example, the situation of a synthetic antiferromagnet, which is basically two layers of a ferromagnet with magnetizations opposite to each other, this would mean that we would need odd staggered fields to switch such a magnetization. And this comes from the fact that the inversion symmetry, which is quantified by this vector z here, is broken in a different way or in an opposite way on the top and on the bottom of the synthetic antiferromagnet. And it is really the honor to work with experimentalists which discover such a material as copper manganese arsenide, who has manganese atoms which have magnetic moment, which is an antiferromagnet, and these two sublattices actually have this exactly inverse sense of inversion symmetry breaking. And our calculations confirm the physics, the magnitude, and the staggered character of the fields which act when you apply a current on the magnetization in such a compound, and therefore can establish a room temperature switching of an antiferromagnet by an electric field, which is kind of the first proof of principle work which brings antiferromagnets into a wider landscape of spin-orbitronic effects, where we know it is crucial to control somehow the magnetization and preferably use the electric field for it. In the last part of my talk, let me discuss with you the vision of ultra-fast spintronics. It is basically 3 more slides. What we want from modern spintronics also is that it actually operates at ultra-fast frequencies. And when we talk about ultra-fast, this means going to a higher class than what we have now, and we have to have terahertz frequencies for operation of our devices ideally. Now, if you think about it a little bit, 1 terahertz is about 1 milli-electron volt. This means that when you have a terahertz radiation somewhere in your sample, which you use for whatever purpose in your device, you actually excite a wide spectrum of electronic excitations. You excite collisions, you excite magnons, you excite phonons, atomic vibrations, and the spin-orbit interaction is also in this regime. Therefore, it is important to understand whether the fundamental phenomena in spin-orbitronics, such as spin-orbit torque or spin-Hall effect, can be brought into terahertz domain. And I will try to briefly answer or to suggest that actually Hall effects and spin-orbit torques can be operational in terahertz regime, while the vision of terahertz ultra-fast fermions is actually still something to tackle and to consider. Okay, let's take a look at the ferromagnet which is brought in contact with a paramagnetic substrate. Let's say we have iron on ruthenium. What we do, let's be rude to this ferromagnet and let's shine some femtosecond laser pulse on it. What happens actually is a complete mess, because it is a situation totally out of non-equilibrium, and actually we cannot really model at the moment precisely what happens with this ferromagnet. However, our experimental collaborators, in particular Tobias Kampradz's group in Berlin, tell us that they see a very large terahertz radiation which comes from this sample. Okay, good. Within one simple model or within one simple picture, what does this femtosecond laser do? It puts the occupied electrons into the unoccupied states. And when this happens, these electrons actually acquire velocities from those, different from those they had in equilibrium in their ground state. And this results in the so-called super-diffusive current, which is injected into the paramagnetic substrate. The magnitude of this current can be estimated, and it can be actually rather large. However, let's ask ourselves the following question. If we have a spin current propagating in a paramagnet, now we know everything about spin-orbitronics, what we would expect an inverse spin Hall to act in this situation. This means that if we have a spin current in one direction, we can generate a charge current in the transverse direction. Indeed, within this simple scenario, this transverse charge current would give rise to this kind of terahertz radiation. However, we have to somehow prove that this is the spin Hall effect which stands behind this. And to do this, our experimental collaborators did a lot of measurements where they took a lot of different samples, different paramagnets. They measured these various terahertz signal, terahertz radiation, the sign and the magnitude, and they plotted this magnitude of terahertz radiation versus our calculations for the spin Hall conductivity of these paramagnetic substrates. And what we discover here is a very close correlation between the two. It's actually perfect. This means that the whole terahertz radiation which we see here is generated by the spin Hall effect in the paramagnetic substrate. This is good news because we can say for sure that the terahertz spin Hall effect is a reality. Okay, let's think a little bit more and let's think of an alternative scenario which can happen when we excite our magnetization with a laser pulse. When we have spin orbit torque, we have magnetization, we apply current, and magnetization starts moving. Now, by using reciprocity principles, when we start moving the magnetization within the scenario of what we call an inverse spin orbit torque effect, we're able to generate a longitudinal electrical current. And using the, for example, Kubo linear response formalism, we can estimate the magnitude of this effect. The expression for this current is relatively easy to derive, and it is directly proportional to the rate with which the magnetization changes in time. Now, an idea or a question here is whether something like this could be also happening in the very same experiments which you have seen in the previous slide. And if this would be happening, we know from symmetry arguments that it would give a different type of terahertz radiation which would lie in a plane which is orthogonal to the one we saw previously. Our experimental collaborators this time from Nijmegen in the group of Alexei Kimmel designed such an experiment which looks pretty much similar to what we have seen before from Tobias Kampfert's experiments, and they shine a circularly polarized femtosecond laser pulse on our magnetization, and indeed they measure this type of terahertz radiation which is distinctly different from the one that we saw within the super-diffusive current picture. This is an example of this measurement, and what we can say here is that from the symmetry arguments and from the estimation of the magnitudes that we can provide to compare to this experiment, we can for sure say that the spin orbit torque works and pumps electrons by magnetization dynamics at terahertz frequencies as well. And I think this is actually great news, which opens the door to terahertz applications of spin orbitronics. Now, the last slide is I basically try to convince you in a short talk that the field of topological spin orbitronics, which is based on Hall effects, chiral robust textures such as fermions, and the effect of various torques, in particular spin orbit torque, is an exciting emerging field in technology and also in magnetism, which is recently combined with the vision of terahertz applications. At this point, I would like to thank the members of my group, which has been working with me for some years, and in this case, in particular, Frank Freimund, Bernd Zimmermann, Jürgen Weichenberg, Philippe Chaya, and our collaborators in Prague, Jakub Zelezny and Jacob Gales. And among experimental colleagues, I would like to thank Hiro Sinova, which is a theoretician, but he entered this slide anyway, Tomasz Jungwirth from Prague, Tobias Kampfert from Berlin, Markus Milzenberg from Greifswald, Pietro Cambardella from Jülich, Alexei Kimmel from Nijmegen, Christian Schneider from Garching. And I would like to thank you for listening to this talk.
I would like to ask a question. If this reverse spin torque effect is in fact present, then can we imagine such a sort of experiment? That we have a ferromagnetic wire with a single perpendicular ball domain wall, sorry. And we are moving this domain wall by application of external homogeneous and constant magnetic field. But
yes,
if the current is produced, we have some pulse. But the magnetic field alone doesn't carry any pulse. So
I'm not sure I understand the question.
The answer is yes.
Answer is yes. Yeah. So the domain walls motion can cause this kind of charge pumping. So that is well known. I think also Garrett and Yaroslav have been kind of suggesting this as well. They working out phenomenologically.
But where is the pulse coming from?
That is the question I don't understand.
I am constantly switching them around.
So you apply magnetic field from outside, you pump, let's say, the energy into the system, and therefore, actually, so you ignite the magnetization dynamics, and then you transfer the impulse to the electrical current.
Yeah. And using topological Hall effect with fermions, but
yes.
Does other magnetic solitons, quote unquote, like
they give rise
vortexes and such produce the same effect?
Most probably yes. However, I think for vortices, they're first of all rather large, right? And the distribution of magnetization there is different from skyrmions. So the physics is different. And so actually I haven't heard any data, or I haven't seen any data on topological Hall effect in vortices. So it's basically in skyrmions, which you can make really small, and you can make lattices of these skyrmions that you can actually generate gigantic fields. Yeah? So the emergent magnetic field that you have in manganese silicide is of the order of 10 Tesla. While if you make it 10 times smaller, it will be order of magnitude larger. Yeah? So ideally you can have hundreds of Teslas of field, which gives you a gigantic response, a gigantic Lorentz force on your electrons. That's, of course, there is a different aspect. They're not only skyrmions, but there are different merons and skyrmions of different charge. But the idea is that whenever you have a kind of chirality or an emergent field or a Berry phase in these structures, you always get some sort of transport manifestation.
And the last question. For antiferromagnets, there are some new ways of controlling them proposed. But can you propose any ways of seeing the changes?
Sure, AMR. So what you actually do is, in this example that I showed, you switch it by 90 degrees. Yeah? And there is a phenomenon of anisotropic magnetoresistance, which also is active in antiferromagnets and in ferromagnets, where you look at diagonal conductivity or conductance and you see the change with respect to either direction of ferromagnetic magnetization or staggered antiferromagnetic magnetization. So you can say that something switched using this AMR effect. And that's exactly what you use, actually.
One more question. As you said, you're probably the best person to ask because you are doing Ab-initio.
Yeah.
And obviously, there are obvious restrictions for Ab-initio.
Sure, there is.
And therefore, the question is, what is the state of the art now in terms of number of atoms? Because usually, most people who are doing this still doing averaging of deterministic scales.
So the rule of thumb is that if you have less atoms, you can go further.
Absolutely.
So this is also true for you, right?
But what is this, 20 million? 30 million? What is that?
Atoms? No,
Yes.
no way. So for Ab-initio, you can treat maybe, realistically these days, you can treat several thousand.
That's it? Well, I've heard, 5 years back, clinic group in Purdue, we're talking about 20 millions.
Sure. So the effects which we study here, they have spin-orbit interaction. They have non-collinear magnetism. And there is absolutely no way that at this current state of affairs you can realistically treat non-collinear systems with spin-orbit interaction for 20 million atoms. Yeah. There is just no computing power for this. So if you treat iron, BCC iron, you can calculate whatever you want. You can go to higher order Kuba response and do fantastic things. For example, maybe in the next talk we will hear about that. But if you stick yourself to like thousands of atoms, then you're already more restricted. You can calculate maybe Landauer-Güteker kind of transport. But to go beyond is then, each order in perturbation is then,
so
3 orders.
What is your limit to the number of atoms in the presence of spin-orbit?
So my personal limit.
There's a memory bottle.
My personal limit. So the systems which I study, let's say from 20 to 40 atoms.
Because I've seen in practice, you try 500 atoms of platinum in spin orbit, the memory requirement is 900 gigabytes.
900 what? Gigabytes, yes. And this is not something which you want to then build on top of.
Friends, I think we should move on. Let's thank